All right, so in the last video, we were just going over the intermediate value theorem. And we haven't really broken down the stuff in this box yet, but we did informally talk about what the IVT is. So I'm going to read the box one more time before we go over these examples. I know you're probably tired of me reading to you, but if we were in class, I would be doing the exact same thing. I'm going to erase the stuff that I wrote on here just to rewrite some stuff on here. So if a function f, if f is continuous on the closed interval a to b, remember a and b are values of x. So again, I'm coming over to this graph I drew. A and b, these are x values, and the function has to be continuous at least on this closed interval. Maybe it's continuous everywhere. I really don't know, but it's got to be continuous from A to B first of all. That's the hypothesis that must be met in order for us to draw this conclusion. So then, for every k between f of A and f of B, there exists a c on the open interval AB, so between A and B, not including A or B, such that f of c equals k. That looks funny to me. All right, so if I look at this, k is a y value. We said A and B are both values of x. C is also a value of x. So for every value k between f of A and f of B, there exists a c such that f of c is k. So I'm going to go back to this drawing, and let's just say that this is a value of k. I'm going to call it k1. If I come over to this function, it's right here. And the value of c would be right here. So there exists some c so that f of c is k. All right, let's say there's another k value. Like, let's call this a k. All right, if I go over to my function, it's right here. So there would be a c there. Maybe here's where k3 is. I come all the way over to my function. Well, I'm not drawing this very well to scale. Then maybe that's where my c3 is. So really, it's just telling us if the function's continuous, the function has to obtain all the possible y values between f of A and f of B, which are also y values. And the x values will exist between A and B. All right, so this will be a little easier, I think, once we practice it. And we'll work with the IVT like all year long. So, all right, so if f of x is x squared minus 4, must there be a value of c? This little symbol means like is an element of, but really we could interpret that as between 1 and 5. So must there be a value of c between 1 and 5 such that f of c equals 10, and if so, find c. So the first thing we need to know is f continuous on the closed interval from 1 to 5? And the answer is yes, because x squared minus 4 is continuous everywhere. There's no domain restrictions. So we've satisfied the hypothesis. So the first thing that I'm going to write is that f is continuous on, and we need to check it for the closed interval, 1 to 5. Now it's continuous everywhere, but that's more specific. All right, so we've checked off our hypothesis. So now we can apply the conclusion. So the conclusion involves us knowing what f of A and B are. So we need to know what f of 1 and f of 5 are. So f of 5 is 5 squared minus 4. So what? 25 minus 4, 21. F of 1 is 1 squared minus 4. So 1 minus 4, negative 3. So the question is this number 10 between negative 3 and 12? And it is. So between 1 and 5, there must be some value of c so that we get f of 10. So first, must there be some value? The answer to that question is yes. So yes, there is, or there must be a value C that's an element of the interval 1 to 5 such that f of c is 10. And I just end up copying that language a lot from the prompt. And then lastly, we're asked to find c. Well, if f of c is 10, I could set 10 equal to x squared minus 4. And I could then add 4 over. So I could solve this for x. So if I add 4 to the other side, I get 14 equals x squared. And then when I take that square root, I get the positive and negative square root of 14. But only one of those numbers is on the interval from 1 to 5. So c would have to equal the positive square root of 14. So if I think about that, the square root of 16 is 4, the square root of 9 is 3. So I know that's like 3 point something. So c would have to be just that positive value. All right, the next problem, if g of x is 3x over x minus 2, must there be a value r that's an element of the number set from 1 to 3, such that g of r equals 10, and if so, find r. So the first thing we need to do every time is check the hypothesis. I can't tell you how many students forget this, and it just kills me because they lose a lot of points. So is g continuous on this interval from 1 to 3? So I need to check this for discontinuities. 3x is always continuous, so I don't need to worry about the numerator. X minus 2 is always continuous, but since we have a fraction, I know that x minus 2, I need to consider where that equals 0, and that equals 0 when x equals 2. So I know that at 2, I'm actually going to have a vertical asymptote. If I plug a 2 in, I get 6 over 0. So the issue here is that g is not continuous. So the way we could answer this question is say g is not continuous on the closed interval 1 to 3. So IVT does not apply. So we cannot say that there is not a value in between 1 and 3. We just cannot use IVT to guarantee it. And I'm not going to worry about that one anymore. Like, that's all I'm going to say there. All right, the next example. We're given P of t, and we're again asked that same question, and there's you'll get in the habit of reading this question and knowing that it's either about the IVT or this other theorem we'll learn about later. But again, I want to check P for continuity. So t plus 2, that's continuous everywhere, so that has the domain of all reals. E to the t is like e to the x, that has the domain of all reals. So the function's continuous. So I need to state that. I can't just assume it. So I can say P is continuous on the closed interval 0 to 1. And then for us to now apply IVT, we need to know P of 1 and P of 0. So P of 1 is going to be 1 plus 2 times e to the first power. So 1 plus 2 is 3. P of 1 is 3e. Don't try to do anything else with that number. 3e is a number. And we like 3e because I don't have to do any other work. All right, P of 0 is going to be 0 plus 2 times e to the 0 power. 0 plus 2 is 2. E to the 0 power is the number 1. So that's just 2. So the question is 4 between 2 and 3e? And we know e is almost 3. It's less than 3, but it's nearly 3. So 3e is less than 9, but nearly 9. So I know 4 does exist between 2 and 3e. So the question, must there be a value x on the interval 0 to 1 such that p of x equals 4? Yes, there must be. Somewhere between 0 and 1, this function has to be 4 because it's a continuous function. So we could answer yes, there must exist a value x that's an element of the set from 0 to 1 such that p of x equals 4. And we were not asked to find what x is, so we're not going to. All right, we'll try this last example. I hope I can wrap it up. How about this actually? I'm going to ask you to pause the video, try this last part on your own, and then resume the video to check it. Okay, so hopefully you had time to work these out. That first question, average rate of change, that's real straightforward. Just be careful with your subtraction of integers. 5 minus -1 is a positive 6 there. And again, you want to try to do these without a calculator. We won't be using any calculators until second semester, really. The second part, so h is continuous. So we could use IVT, but here's the problem. Look at the table between 0 and 2. At 0, the function h is at -3. At 2, we're at 2. And at 1, we're at 1. So we can't guarantee that there is ever a value of +3 since the function doesn't, like h doesn't obtain a value greater than +3 on that interval. So even though it's continuous, IVT does not guarantee it. You want to be careful that you don't say that no, there's not a value. There could be. Like, we don't know what's happening between 0 and 1 or between 1 and 2. We just cannot guarantee the value using the intermediate value theorem. The second IVT question, though, is a hard yes. So h is continuous on the interval 4 to 5, the closed interval. It's continuous everywhere, but we would confirm on the closed interval 4 to 5. So we can apply IVT. And what we need to check is, first of all, h of 5 is 5, h of 4 is 1. So we need to write that out. The number 4 that we're guaranteeing is between those two numbers. So that's why this one is a yes and the one above was a no. So it's between those two numbers. Since 4 is between h of 5 and h of 1, or between 5 and h of 5 and h of 4. I made a typo right here. That should be a 4. Or I could think of it as being between 5 and 1. Because of that, we can guarantee that there must be some value of p between 4 and 5 so that h of p is 4. All right, this last one. How many, at least how many zeros must the function obtain? How's that worded? It's going to have at least 4 zeros. So again, we said it's a continuous function. So if you look at the h values, to go from -3 to 1, you have to pass a 0 on the number line somewhere. To go from 2 to -1, you've got to have a 0 there somewhere. From -1 to +1, you have to pass a 0. And then lastly, from 5 to -3, you have to pass a 0. So at least 4 zeros. Now, there could be way more zeros. The function could hit 0 a bunch more that we just don't know, but it must be 0 at least 4 times.